So why do we have any interest in studying populations? We know populations change. So we look at the flexibility of populations. So change, and really change over time, right? We also want to know in general what's going on with these populations, so that if a population or an ecosystem changes, what effect is that going to have on the population? So knowing the population's size and distribution, so how far does it spread in an area, is really important for scientists to understand if we're going to make predictions about changes in these populations. We've got a couple of options as far as population growth patterns. We have arithmetic, so if we look at our car example here, it's showing us that between day 1 and day 4, we've added 3,000 cars. So if that's per 3 days, we're adding 1,000 cars per day. And we do that every single time, okay? In the end, at day 25, we have 25,000 cars. That should make sense if you're adding 1,000 cars per day times 25 days, right? Exponential growth, on the other hand, is what we see in a lot of populations, particularly the arthropods, invertebrates, organisms like that. So between day 1 and day 4, it's actually only added 1,000. But between day 4 and day 7, it adds 2,000. So if the population doubles every 3 days, by the time you get to 25 days, you actually have 256,000, in this case, Daphnia. Huge differences in population growth, right? We have to know how populations grow in order to understand any changes that might occur in the environment that would impact those growth rates. So if we start out with 0 over the course of our 25-day period, as we showed you on the table a minute ago, we have huge growth associated with this exponential growth. Yes, arithmetic growth is important in that you are consistently adding the same number of individuals, in this case cars. Exponential growth, though, we would expect very different things from those population structures. We see exponential growth in other organisms as well, things like rabbits. The exponential growth in rabbits, we look at the population increasing from about 25 individuals to 475 individuals over the course of 12 months. These are huge growth patterns, right? We also see the same sort of pattern in breeding fur seals, increases from about 1,000. Now this is over a much longer period, right? We have to think about gestation period. A Daphnia, like we saw before, reproduces every 3 days at most. When we look at fur seals, we're only looking at reproduction maybe once a year. So to truly see increases like this in growth patterns in a population, you really have to focus long term and on the entire population. How many pups are produced every year, and how does that impact the next year's population? Are conditions good? Are they surviving well? But one thing we do have to consider is that with our rabbit population, we tend to see it continuing to increase over and over and over again. So this is something we refer to later as a J-curve, as opposed to our fur seals that produce something known as an S-curve. You notice that our seal line here is capped by this letter K. K is carrying capacity. I know, carrying doesn't start with K. I'm sorry. But that's how we label it. So when we look at this S-curve, or this carrying capacity limitation, what we're saying is the planet can really only sustain, or this geographical area can only sustain, that much growth. So there are limitations: habitat, food. Something is limiting this population. Rabbits don't have those same kinds of limitations. They're smaller, they reproduce faster, so different stresses on those individuals.